Good, thank you. So we continue second talk this afternoon on pulse laser deposition given by Professor Mark Huijben from Netherlands.
Thank you. Well, in this talk in the afternoon, I would like to show you a specific synthesis technique. So pulse laser deposition. When we look at oxide materials, there are several techniques which are used a lot and which enable you also to make these oxide systems in a very controlled manner. At University of Twente, we use pulse laser deposition a lot. We have a research lab where we have 10 different PLD machines to our use. It's also a lab which is being used by several different groups. So here you can see all my colleagues. Professor Reijnels, Koster, Morales, Massis, Hilgekamp, Brinkman, and Bijkerk. And all of them make use of PLD. Some of them, I would say a lot, some of them a little bit less, but it's a shared facility. What I would like to do today is to show you a little bit about, let's say, the general aspects. Maybe some of you are very familiar with this and some not. And at some point I would like to go into much more specific examples where you can go to, I would say, using this at the most advanced level. Or maybe some of you are doing that as well. The thing I would like to mention is that as we, I would say, have a group of researchers using PLD intensively, we also every year have workshops on PLD where we invite students from all over the world to come to Twente for a week and being trained in our lab, hands-on experience, with lectures from us, practical examples from us, but also companies will be there which are normally involved in the read, are in the equipment and these kind of things. So if you're ever interested, just contact me or anybody else over there. Now if we talk about pulse laser deposition, it's clear, it's a laser, it's pulsed. It's even difficult sometimes to keep it on the camera, but here you can see on the left side the heater which is warm and on the right side the target which is being ablated. Now maybe the things which are a little bit more easy to show are these kind of animations, where you can see that the laser is UV, so you don't see it, and then you switch between different materials and you're able to build up an artificial structure. And we always talk about this, about playing Lego. And we're building up a piece of material which is, let's say, not available in nature. Now over here you can already see that if you want to be able to do this, you need to use pulse laser deposition at the most controlled way. You really have to be able to tune the individual thicknesses of the materials. So that's where in the middle, you can see the read pattern. We'll come to that later, but you use electron diffraction to do that. But within the materials, you would like to be certain that the stoichiometry of your materials are correct, that the oxidation of your materials are correct, that at the interface between the two materials, there's no intermixing, or hopefully the minimum amount of intermixing is happening. And that requires a lot of knowledge and specific expertise. And what I would like to, or hope to be able to do, is to show you a little bit about the general aspects which maybe you could use for your own research. So as a starting point, can you raise your hand who's using pulse laser deposition in your own lab? Okay, a large bunch. So probably when you started studying your oxide materials, you looked in literature, you see, did anybody else do this before? You took the paper and see if you could reproduce it. Who of you struggled with reproducing that result from literature? Yeah, there you go. Me as well. On Saturday, I will show in a different talk about lithium-ion batteries, lithium-ion oxides. They have been published about some of the material. It took us 2 years to reproduce this. I thought our group had a lot of expertise, but sometimes, let's say, the parameters that you need to control is not completely clear. It's not only temperature, pressure, and a little bit of fluence, but that's only the starting point. So it's very tricky to be able to grow exactly what you want, and it really depends, of course, on the material that you're looking into. No, so playing Lego is what we're talking about more often. The interest for these kind of techniques is because you're able to grow complex oxide material. There are a whole bunch of techniques which allow you to grow, I would say, the more simple oxides, but pulse laser deposition, sputter deposition, but also MBE, there are some of these techniques which allow you to go into the more complex materials, and they go all over the scale from the different functionalities. And maybe some of your materials in this list. But you have a lot of different things to choose from, and in the end also to combine them in an artificial stack. Now when you look back, when people started using pulse laser deposition, before they were using the laser to, let's say, hit a surface and there structurally deform the material. They only started in the 80s to use pulse laser deposition to really ablate the material. This was and copper oxide, to grow thin films of this interesting superconducting material and see how they could create superconducting thin films and study their performance. So this is in, I think, 87, and there on the right, now you can see the resistivity line drop at a temperature that it becomes superconducting. So that was the first moment when they really started using pulse laser deposition. And what I circled here in the middle, it was an indication at that time about the target they used. They used a single bulk material, so they used the target which already had the correct phase in it. They didn't use a target where you had some yttrium oxide, barium oxide, and copper oxide and just ablated it. They already indicated it was more important to have a target which had the correct composition but also already the correct phase. And I will come back to this point, but if you are studying oxide materials and you're looking into papers about how did they do this, very often it's not very well defined about what kind of target did they use. That's where it goes wrong very often, because it's clearly different than what maybe you are using as a starting point. And it's not clear who used the best one, but it's not the same. It makes a lot of differences. So if you think about pulse laser deposition, and people are mentioning some of the features that it has, a clear thing is that it's relatively simple, although, as I indicated before, I'm saying it's not always simple. To have a transfer, stoichiometric transfer from the target to the film, you can tune the kinetic energy of the arising particles on the surface, and you can play with the background gas and things like that, or with the kinetic energy on the surface with the temperature. Each deposition pulse, you have a high supersaturation. I will go into this more detail later. And you can see it's instantaneous deposition, which means that you deposit your material on the surface, then there is no material arriving, but then the processes on the surface happen where diffusion starts, where nucleation starts, and where the film will grow. And it also allows you to study independently, first when you deposit the material and later the growth process itself, because it's pulsed. And this is also where you can see here in the bottom part, if you look to the diffusion energies, the diffusion processes, when you look for complex oxide, you can see there the activation energy and the temperatures at which a lot of deposition is happening. And you would calculate what the diffusion time is over surfaces. Then you can see that the deposition is done, let's say, in 100 microseconds, roughly. But then there's a much longer time for the diffusion over the surface. Yes, you had a question?
Very short question. I'm not used to this technique. Can you show on the picture where is the target and where I'm...
Oh, sorry. So what you can see over here, from the right you can see the UV light coming in, that's the laser. Okay. And then this is the target. So there are 5 different targets, 5 different materials. And it's being, let's say the light is interacting with the target. There all the energy is absorbed, it becomes extremely hot, and then the plasma has created all the particles, then they're ablated from the surface. This is where you have the plasma, and the plasma is moving forward towards the heater. We're in the middle of the heater. You have a crystal, a substrate of interest where you want to cover your thin films on top. And then I will go into later, but here you can see a tube where the electrons are coming out, they're interacting with the surface. Diffraction will happen, and this is a phosphor screen where you can see a pattern of the electron diffraction which is happening there. And behind this screen is a CCD camera which will take pictures of this screen and bring it to your computer so you can really monitor the growth while you do this. And there are here 5 different targets, but it really depends. If you want to grow a single material, then only one target is sufficient. But if you want to make a stack of, let's say, a multi-layer, then you combine several of them. Yes?
When you say 100 microsecond for a single layer?
So this is for a pulse. So let's say when the laser hits your target, this is about 20 nanoseconds. Yeah? And then when the material is being ablated, so when the material goes towards the surface, this is, let's say the deposition is in about 100 microseconds. And then the diffusion over the surface can be seconds, can be up to a minute.
Yeah, but I mean the thickness you can reach with a single...
With each pulse, you mean?
Yeah.
Well, it depends. So let's say if you need a specific energy to ablate material from a target, so I'll go into this, but depending on the spot size on the target, that will define how much material that you ablated. And roughly, what we normally do is about, let's say, 30 to 40 laser pulses for one, let's say, unit cell layer. So each laser pulse is, let's say, 2 to 3% of a monolayer. That means that if you stop at a specific point in laser pulses, you can get close to the maximum, to the 100%. Let's say if I ablate only 10 pulses for a monolayer, and I stop at 10, I can have an error of 10% because I go over it or I'm not a little bit before. So it's better to have a higher number of pulses. Yes?
What was new in that equation? The freak?
Oh, it's a hopping frequency.
Okay.
I didn't go into this, but this is, yeah. Yeah, so here you can see again the schematics. You have a laser, you have an optics path. In the optics, you can vary the distance between where you have a mask of a specific opening, specific size, and where you have a lens. And when you are having a large distance in your lab, you can play with this so that you also can tune your energy density quite a lot. So you can go, let's say, from half a joule per square centimeter on your target to something which is about 5 joules per square centimeter on your target. And that's necessary if you, for instance, go to metal ablation. There you need much higher energies. That's where you also need much higher fluences. If you bring this very close, then you only have a little bit of distance to play with. So if in your lab you're only focusing on a few materials where you have these settings, it's fine. But if you want to cover a lot of different materials, then you need more space to move this around. Yeah, and then you have a lot of the growth parameters. So the things which are normally published in papers, or sometimes are not published. Sometimes one of these things is missing, so you want to reproduce it. You say, okay, they don't mention spot size, or they don't mention, for instance, they mention the laser energy, but not the laser energy density. They don't mention the spot size, so you don't know exactly what is happening there. And I'm not going into the topic over here, but as the energy density will define how easily that you ablate material from your target, you need to overcome a specific threshold before the ablation is done homogeneously. And this is something where I normally suggest all the students to start with. If you have a new material, if you have a target, don't start growing thin films immediately. Put it in the system, ablate it with your laser, make several spots, put it under the SEM, and look at those spots. If your laser energy is too low, you will have pillar formation. Because on the surface something is not ablated, and then the next pulse, this is shielding everything else. So it forms a pillar, and at some point it breaks off and it becomes a particle on your surface. And only at, let's say, 2 joules per centimeter or something like that, you will have homogeneous ablation. Ablation looks like it's melted, and above this, it will stay this homogeneous. But then you define what the fluence is for your target. And this is different, can be different for every target. So you need control over these parameters. As all our systems in our group are pretty much the same, we can transfer these parameters from one system to the other. So that's very helpful for us. But if the system is different with the design and everything, and even if you use then settings from different groups from papers, that's not automatically successful. Now, as a starting point, we heard about this already a lot. So perovskite, strontium titanate, you start with the substrate. Here you can see the cubic crystal structure. Of course, this is helpful if you want to stack different kind of perovskites on top of them that they form, let's say, a similar building block. But if you want to use them as a starting surface, you would like to have, let's say, a surface which is single terminated. So that at the surface you only have either this one, where you can see this is titanium with oxygens, and over there this is the A side, let's say strontium with oxygen. And they are forming different layers. So what you can do is if you have strontium titanate, maybe this is known to many of you already, so you can use a procedure where you do them in water. You form strontium hydroxide, you use HF, you can remove this strontium layer, then you put them in the oven, you anneal them, and you get a nice terrace surface. When you put a line profile on it, you see these terraces, and you can see that each one of them is a unit cell. If you want to achieve the opposite, the strontium oxide termination, you cannot do that by chemical trick. You want to deposit a monolayer, and the deposition of that can be done by interval deposition, which I will show you in a few minutes. But then you can deposit a single monolayer, and here you can see the AFM pictures. It looks pretty similar. Then at least you can achieve the single termination, which is the ideal starting point. If you don't do this and you just put your samples in an oven, they become smoother, but they will never be 100% single terminated. At the step edges, you will always have a double termination. Now, this is how one of our systems looks like. Yes?
In the last figure, when they make the strontium oxide terminated, how they make sure that it's strontium oxide?
Yeah. I will show later, but if you do interval deposition, it means that you deposit the ion material at a high frequency, as fast as possible. So it means that if you do electron diffraction read, you have a high intensity, so it's very smooth, and if you deposit something, the intensity will drop. And in interval deposition, if you then form, let's say, a closed layer, the intensity comes up again.
So my question is there any other characterization they are doing it to make sure that this is strontium oxide other than the read?
Strontium oxide? No, we deposit strontium oxide. We know it's strontium oxide. The question is, how are you controlling that you deposit exactly a monolayer?
Yeah.
So this is where with the read you can follow the deposition. It comes back. Later you can do AFM to study if it's a closed layer or not. And if it's not a fully closed layer, with the deposition of some other materials on top, you will see the difference when there is still some of the other termination available or not. It will form a closed layer or it will form some structure. But it's a tricky process because you need to exactly deposit the number of pulses with, let's say, 50 Hertz at once. So this is a very crucial optimization. So this is one of our systems. This is not only the PLD, that's the one here, let's say on this side. No, this is the E-beam evaporator, this is not MBE. Here you can see the XPS, UPS system at the back, and then there is a connection to this side, where in the past there was an AFM STM connected. We removed it a couple of meters in the lab, and now there is a 4-probe system available, where you have 4 different AFM STM probes, where you can probe it onto, let's say, nanowire and these things, where there is a SEM connected to it. That's a whole different story. That's difficult by itself, where we have people only focusing on making this possible. But you can see then you have a cluster system where you move your samples in vacuum, so to be able to do all this analysis without breaking vacuum. So here, again, laser beam, target holder, beater, and as I will go into this electron diffraction a little bit more deeper, here you can see where the electron gun is located. This is the phosphor screen where you make the pattern. And you can see here that there is a long tube where the electrons are going through before they go into interacting with the surface. It means that they're traveling only a short distance through the oxygen environment. Because normally these electrons are scattered at high pressures when they interact with these oxygen molecules. And only now when you have this tube, you can do this. But the development which was done in the 90s is that where you require a low pressure in the gun, you have a high pressure in your system, you need this two-stage pumping to go from high pressure, intermediate pressure to low pressure. But this is, I would say, now being used in a lot of places in the world. That works very well. And you can see, as I was shown before, how you can switch between this. Of course, normally you don't provide a single pulse. If you want to mix materials, you would, but I think you would like to grow more into layer. So if you look then on this cluster system from the top, you can see that over there, that's the electron gun. And here in the black box, you have the CCD camera. And this is how a normal read pattern looks like of a strontium titanate surface. And what you see in here is the surface of this titanium dioxide terminated STO with these unit cell terror steps. And if we look in detail, this is, let's say, the shadow of the substrate, where you still see a little bit of the direct beam, which is not being diffracted, but which goes straight through. And then you can see here the diffraction spots. And the one that we're normally focusing on is the one in the middle, the specular spot. Although I must say I see more and more students in our lab to monitor all the different intensities. You can. Computer allows you to do that.
What would it mean if you monitored the intensities of different spots and they're out of phase with each other in terms of the oscillation?
Yeah, so what it will show is that if you look at this spot, it will tell you about the crystal structure, at which location will show, but the intensity will tell you about how smooth the surface is. So you really follow from high intensity, low intensity, high intensity. If you look to the side, if you would not focus over here, but you would focus next to it, you would see the inverse, because what happens is that the spot will drop in intensity, but will come wider. So where you would see, let's say, the inverse, sometimes that happens, but it tells you about the alignment of the reed. So it's either you look at the spot itself, or you look at the diffuse region. Now, and it's not so clear in this picture, but you will, if you look at the smooth surface, you will also see Kikuchi lines coming from this point. But you have to believe me on that. So this is what I told you before. You have a laser pulse. You have the laser pulse is very short. This is about 20 nanoseconds. Then you have the deposition of material on the surface, which is maybe 100 microseconds. And then you will have on the surface, you will have the amount of material which is diffusing. So first you have the supersaturation, the amount of material which is increasing rapidly. And then you will see that over time the material is able to diffuse over a much longer time, which you could control, to form a very smooth surface. And that also allows you, as they're separated in time, when the pulse is over, to maybe study something on the surface, to study what's happening there. How is your material forming? And this is also what's being done, not only by Reed, you can do that, but also we and some others have done this in the past, where you can do surface XRD. And then you can really study the growth. The problem there is that these kind of studies are done in a synchrotron, and not everybody has a lab available to do that. So in the past, within a week, we built it up, a PLD lab over there, did some measurements, and we took it away. We don't do that. It's not ideal. Well, if you look into the growth of films, you can see it from textbook. You can think about different growth modes. Things which are either growing layer by layer. You have something on the right which forms islands, and you can have something in the middle, which is a combination of both. And here, it's really an interaction between the kinetics, so let's say diffusion of your material on the surface, and the thermodynamics, the energy, interaction energies between the two materials, which is something you can control. So these are the growth modes which maybe sometimes appear. But we'll go a little bit more into this, because what's happening at the surface is that when the material or the particles are arriving, a lot of different processes can happen depending on your parameters. So either some material can re-evaporate if you're using higher temperatures, because that's where your material crystallizes, there will some evaporation occur. It will diffuse over the surface, it will find other particles, so they will nucleate, they will cluster, and in this way something will build up. And it depends on the energies, if they really will stick on top of the islands, or they have enough energy to move over the edge and go to the surface, so they'll really form something layer by layer. Now, an important point is the kinetics in there. So how much energy do your particles have, or how much do you give with the temperature which is on the surface on your heater? So you can think about the transport over the surface in two ways. Either the intralayer mass transport on a flat surface, as over here, or the interlayer. And the interlayer, I mean when it goes from, let's say, one surface over a step to the lower part. And if you model these kind of surface diffusion and growth of layers in the kinetic Monte Carlo simulation, when you have to involve all these different energies, so you can here see, let's say, energy indicated for something to diffuse over a surface. If it has to move from this side over an edge, then you have to use an extra energy term, as indicated over here. Because at the corner, the coordination is reduced, so it also has to overcome a slightly higher energy. And if you put this into your modeling, you can really nicely model let's say, the thin film formation of specific materials. Now, these different energies of diffusion over surface is something that you can experimentally get from the read, from the electron diffraction, as I will show you also in a minute. So that means that if these kinetics are involved, and these two intra and interlayer mass transport, then you can see here also 3 examples where in the middle you really have layer by layer growth. So the material can diffuse, but at some point you will see that you have these formations, and the next element is able to go in between to form a closed layer before you have the second layer forming. But here on the left you can see the so-called step flow growth. So all the arriving materials have so much energy so that when they arrive to the surface they are always able to move to the step. Which means that in read you won't see oscillations, but you will see a constant energy and it will always be smooth. So as many of you probably are looking into, can I grow something layer by layer? I would say this is even better, because there you have a very smooth surface which is staying like this. But this is not possible for all materials. On the right you can see if you don't have sufficient energy that it will just pile up to become a multi-layer system. And here at the bottom you can see the effect of the temperature and deposition rate, but here the temperature on these different growth modes. So low temperature, of course, you have these island formation. High temperature, you have something layer by layer, but if you go to really high temperature, for some material you're able to go into the step flow regime, which is, I would say, as good as if you could achieve with layer by layer. The only thing is you don't have oscillations which help you to tell how many layers did I deposit. Now, as an example, we grow strontium titanate. We do this by homoepitaxy. Strontium titanate on top of strontium titanate should be perfect. So let's see what happens if you do two-dimensional growth. So the top is read data, which I took when I was a PhD student. The bottom is an animation. And you can see that the read, with all the pulses, is going down, coming back up again. And here there's data for 4 oscillations if everything is going well. But what I will do, as you normally do in the lab, I will stop it in the maximum. Somewhere over there. It doesn't stop. That is not very helpful. But you can see that if you do something in this layer and the intensity comes back to the original intensity, you could imagine that you form something which is perfectly flat. And this is where you can see this. So in read, you have something flat. You can see how the interaction is happening on the surface. The electrons are only interacting with your material within the first few nanometers, so it's really surface sensitive. And you can see when something is roughening up, the next material has enough energy to fill up the holes first and form a closed layer before going into the second. And this shows you from going from high intensity, low intensity back to high intensity, and you form one unit cell of the material, one charge neutral layer. Now if you zoom into the different pulses in the read, you can see here how this goes down and comes up. And here with each pulse you can see when the pulse is given, then within the time you can see that the read intensity comes up a little bit and then flattens off. And this relaxation time tells you exactly the energies which are involved, which you can also use in your kinetic Monte Carlo simulation. So this is where you can really extract the interaction between the different materials. And this is different depending on where you are in your growth. Because in the beginning it's interaction with your substrate maybe, and here you are in a 50% coverage, so it's different than when you are at a smooth layer. Now this is something you can also model. So I will only show you the basics. So what you see here is if you look into the diffusivity and all the different parameters which are involved. So you can see the activation energy, temperature, Boltzmann constant, and here you can see the hopping distance and also the hopping frequency. And if you know these numbers, then you can really look into what is the diffusion length that you expect, what is the diffusion time which will happen at the surface. And some of these parameters with these entities you can extract from this electron diffraction. That allows you to relatively simple model, the growth material. I won't go into detail about this. So this was work by Guus Reinders when he did his PhD work. This came from his thesis, but I think it's also published. It's certainly also in some of the books on PLD, which I will show at the end, so you can look it back. But what's done here is to look into the diffusion of material when it arrives on an island or when it arrives in between the island, and how that influences the number of steps. Because if I tell you something about I have something smooth or I have 50% coverage, it means about how many steps are on the surface. When something is smooth, there are 0 steps. When something is 50% coverage, there's the maximum number of steps. So it's a step density, which is interesting. And that's what you can see here. I deposit a single layer, I go from 0 coverage to 1. It means that the number of steps goes from 0 to a high number back to 0. And if I use the modeling, you can see this is the intensity profile that you expect. And this shows that let's say the lowest intensity is not at 50% coverage yet. So if you look into your read data, you will see this. So I think here, a little bit back, if you look from this to this, you can also see this point is not at 50%. Now, this is also coming directly from the modeling. Now, what happens if I use a temperature which is not high enough? You don't have sufficient energy, diffusion is not optimal, you will see, let's say, island formation, as some materials are arriving already when the former layer is not closed. So here you can see intensity goes down, although you have oscillation, but it's going down, and you can see that several steps are visible. But I won't be able to stop it in the maximum. The one thing which you can, so for some material this is always the case. You can never make it perfect layer by layer. You will always have some roughening, although you see a little bit of oscillation in the beginning. With these oscillations, you know roughly how many laser pulses do you need for a unit cell layer. And then you can do this. You can do interval growth. An interval deposition, it means that you know how many pulses roughly you need. You deposit them with a high frequency, let's say 50 Hertz, and you deposit them at once, and you wait. It means that you provide all the energy or the material which is necessary. They only need to diffuse over a very short distance to meet all the other ones and form a closed layer. They don't need to diffuse over large distances. So you have a lot of material, supersaturation goes quickly, and then afterwards you have the growth. So in an animation it will look like this. Again, the top is real data. So you can see you deposit all the material at once, and you can see the read intensity comes back to the original level, where before it was going down for these growth conditions, for these parameters. Now, and this kind of interval deposition has been used in the past also a lot to build up multi-layers, super lattices of materials with specific thicknesses, which by, let's say, low frequency deposition would not be possible. So here you see pulse laser deposition, how this is normally happening. You just provide material at 1 Hertz or 2 Hertz or 10 Hertz. Depends really if this is crucial for the material that you're forming. You have some high supersaturation. You could have island formation, but with sufficient energy they can rearrange after the pulse. And you will have this interlayer transport. But for some materials you will have the nucleation on top of the ion. Yes?
Would you say that finding out if your material only grows by islands is like trial and error, even if there's literature that, like, if literature doesn't necessarily say you should do this interval deposition, but if you only get island growth? I would say normally, so if you first define for yourself what is the energy density which you have to relate to target, and then either if you have some literature, of course you can always use this to look at what is the temperature and pressure range at which my starting point would be fine. But I would always use, let's say, the slow deposition of 1 or 2 Hertz to see what's happening there. Not immediately start doing this. This is only this interval deposition could be a solution if the other ones fail. And not do it immediately, because that also requires some optimization. And so this is what normally is happening, but if you see this, in home destruction, if you grow one material on top of the other, which you would expect to happen perfectly, if you grow
a different material on top of, you take STO, you grow something else, the crystal structure is different. You will never expect to get at the same level, or you have to retune your reed. So then it's very normal to see a drop because the reed is not perfectly aligned to the new thin film you've grown. So that's a different case. This is for home wave test. And this could roughen up a little bit if you do that, and then you have the option to do interval deposition. And where everything is done at once, and only it needs to diffuse over short distances. I already told you about target. You need to check a target. One other thing is the composition of the target. I said if you are interested in materials, it's always best to have a target which consists of the phase that you're interested in, because then if you hit it with a laser, everything is ablated, and a specific energy is required to let's say, to create particles of it. If your target exists about different phases, they could have different energies which is required to make them into a plasma. So it would mean that maybe only part of the target is correctly ablated. If you have a target with the correct phase, then you would like to have the highest possible density. Let's say 90%, 95% is ideal. But I don't know how many of you are using strontium ruthenate. 60% is about the number that you can get for that target. It's not ideal, but it's the highest possible there. It's a very soft material, and the density is poor, but that's what you have to deal with. And you can still grow nice materials, but normally we would never accept these densities. You need it to be as high as possible. The other thing is, for some materials, if possible, start with a single crystal. So if you, for instance, this was a study. I was a long time ago, I was a postdoc in Berkeley. We were collaborating with several groups, and at some point they came to us saying, okay, we were looking into strontium titanate growth, and we're studying the quality of this growth by looking at the thermal conductivity. It's not conducting, so we need to measure something else. Let's look at the thermal conductivity. If something is structurally very perfect, thermal conductivity is very good. Now here you can see the black line. That's where the single crystal is. So it has a thermal conductivity in, let's say, something about 60 maximum. And what they did was they studied samples made by MBE and they studied samples made by PLD. And what they were looking into to get samples from more groups, and this is what they had here, the MBE samples, and this is where the PLD was. And they said, okay, you can clearly see the difference between the techniques. MBE is better. And we said, okay, we made a few samples, and these were where our samples were. And in the end, it turned out the difference was the target. We used a single crystal target before they were used let's say a solid state target which was made out of powders. And it made a huge difference. We didn't look detailed what was the exact difference or what kind of defects which were formed, but I'm only telling you this can be very different. So also if you achieve some results which are different from literature, think about the target that you're using. The other thing is, as an example of diffusion over a surface, bismuth ferrite is a multiferroic material, ferroelectric, piezoelectric, mentioned in the previous lecture. Volatile element bismuth, so it's not that simple. But normally, if you make this and you would like to study it, you do something, you put strontium ruthenate underneath, electrode material, as you were indicating, and it grows beautifully. If you don't put strontium ruthenate underneath and you grow directly on your substrate, this is what you get. When the BFO is 2 nanometers or 10 or 30 or 60, you get these blocks, you get these square-like features, because the diffusion of BFO on the titanium oxide terminated surfaces is poor, and it forms these layers. But on strontium ruthenate it's very good. It's also perovskite. So what we thought of is, let's switch the termination of the surface. Let's do this interval deposition of strontium oxide monolayer to only switch this atomic layer, and then see what happens. And we did this, strontium oxide termination, and then you can see surface steps. Because diffusion of material on the strontium oxide terminated surface is much higher than on the titanium oxide terminated surface. So when you look into BFO then on this surface, this is on titanium oxide. It has all these square features and the domains are small and not that nice. This is on strontium oxide, and you can see all those very long stripy domains which everybody is studying to look into the domain formation. And then we thought about, okay, why would this only work on strontium titanate? So BFO is also being deposited a lot on the scandates, as it has a closer match. So that's what we did the same. So we used terbium scandate in this case. We used here the B side, scandium oxide, and you have these very small lines which are formed with some high differences, and then we could see those small domains forming. But if we deposit also strontium oxide there, we didn't deposit terbium oxide, we had a target with strontium oxide, again we see the steps, and we see those very nice bigger stripes occurring. So this is a trick that we're using in our group for a lot of different surfaces. So if we see in the growth that the material is not diffusing very well and it forms islands very quickly, we try to deposit this strontium oxide monolayer and see how this improves the growth of any material. The question is also if other A-side, other, let's say, oxides, and not only strontium oxide, but how would calcium oxide or barium oxide happen? I wouldn't know, but this works very well. Coming back to our system, you have a closed system, you would like to do a lot of measurements in your own lab. Yeah, we already took out a wall so that we have a little bit more space, but in the end you're limited. So what we do, of course, we have a vacuum suitcase, so we put our samples in there and we travel within Europe. We're not flying yet somewhere else, that's a little bit more complicated. But these are Omicron based systems, so we can put samples in there, something like 10, 20 samples, and then you can disconnect it, you can go to another lab where you have the same connection and you can study them. So there are now these connections in Berlin, Paris, and Amsterdam, a lot of different places. And this is now increasing to see where some of the material that we're creating then also can be studied without any contamination. If you do PLE, we're looking into creating plasmas and depositing material. And we're trying to control all the parameters, but one thing that we don't study is the plasma. Ideally, you would like to know about what are you creating in the plasma before you're even forming any thin film, and to do a lot of trial and error about what's the temperature and the pressure that you can do. This was a project which ran a couple of years ago, which started then, and we're still using these cameras. So you can see a CCD camera which looks into the deposition chamber. And what you can do, you can really study the plasma which is created when you ablate a target, and you can follow it in space. You can follow it in our chamber. And what you're looking into, as I told you about what is the energy that we hit the target with, what is the fluence, what is the pressure in the system, do we put oxygen or argon in the system, what's happening there, so what are the plasma characteristics which will influence the film growth. And in the end, this is what you would like to know. You can play with all these parameters, pressure and oxygen and everything, and find out if it works. But ideally you would like to know what's happening in this plasma already. So one thing is the propagation. So what you can see in here is the front of the plasma, which starts at the target and then it moves forward, and our ether is normally positioned 50 millimeters away. So when you use a low pressure, it arrives there pretty quickly, and when you use a high pressure, it takes much more time. And there are different models to fit this. And you all know that depending on these pressures, you will give it either more time to, let's say, oxidize, but you will also tune the kinetics. You will also play with the energies that particles arrive. Now, so you can really see the dynamics in the plasma. But more importantly, you would like to see, for oxides, the oxidation state. So here you can see the plasma at a normal deposition pressure of 0.1 millibar. And these are an energy range, as you can see there on the right. And here you can see it starts from over here and it moves forward. And not everything moves as fast, but it's the same as this one, but now it's, let's say, where you can see the different energies which are involved. And here you can see how this looks like from this picture. So here you can see at the different energies at 0.1 millibar, after 2 microseconds, 5 microseconds, and 9. You can see in the beginning there are much more intensity on the left, which are the individual strontium and titanium elements. But later in an oxygen environment, you can see the right part becomes much more intense. That's where you have the oxidized species. So you can see in the plasma, your material is being oxidized before it arrives to the surface. If you do it at a lower pressure, 0.01 millibar, everything stays on the left. You have metallic species arriving on the surface, which hopefully oxidizing whatever you want. but that's not always possible. So that's why you need sufficient oxygen pressure in your system, because for most of the material this needs to be oxidized already in the plasma before it arrives at your surface to get better thin films in the end. So you can play with the kinetics, how fast it's arriving there, and the energies, but you can certainly also play with the oxidation state. So as an experiment, home-wave texture growth, strontium titanate on strontium titanate, and if you do that at different pressures, very often you will see your deposition layer, the peak is next to your substrate. Means crystal structure is not the same, something happens. And what you can see here is if you do your deposition at lower pressures, in this range, the peak is on the left, so the structure is bigger, there are more oxygen vacancies. Even if you bring up the pressure, you will see that the peak is exactly underneath your substrate peak, fully oxidized, correct phases formed, and this is how you would like it to be. And if you do TEM, you can also look into the defect formation that I'm going to do. So here you can see exactly what this oxidation is doing. And this is what I showed you before. But now you're playing with two things with this pressure. You're playing with the oxidation that you allow, but you also play with the energies at which it's arriving. So what you could do is say, I would like to have this pressure, 0.08 here. This is perfect. But now I use this pressure, but only part of it is oxygen, and the rest is argon. So now it gets the same energies, because it's blocked because of this pressure, but the ratio in oxygen to argon tells you something about the oxidation. And then you can see if it's fully oxygen, it's fine. But if the amount of oxygen in the total is reduced, again you can see the shift. Oxygen vacancies are from different structures. So this again is where, if you are creating your own oxide materials, think about it, what is ideal. Okay? Ideally, you don't want to drop your pressures to very low pressure, because then your material is really bombarding your surface. You will never create something which is very smooth. Then it's better to go to higher pressures, but with a large amount of argon in it, and only a little bit of oxygen to make a small flow that your system would allow. And at the same time, it's not only this which is happening, but very often you can see that only at a high pressure something is very smooth, and at lower pressures you have much more 3D formation. Now here are these things, and here in the plume at these high pressures, again you have a lot of these intensities on the right, the oxidized species, and here is most of it is on the left, where you still have these metallic elements. Yes?
Can you change your plume, or at least the way it interacts with just the substrate based off like, the wavelength of light that you shine on it by like exciting it in situ?
And you want to excite the species in the plasma?
Yeah, or is there a tangible effect to that?
I know of experiments where you shine light on the substrate, and there where it interacts with the substrate, where you could create charges, where the interaction is somewhat different. The specific spots or lines over the surface. But I haven't seen a lot of studies on that. Maybe one thing to point out, so this is what I've shown you for strontium titanate, going from, let's say, initial ablation to later on if you fully oxidize it. If you do that for the two individual targets, strontium oxide and titanium oxide, you can see the difference, but it's also not that this is a summation of those other two. It's a clearly different situation. So if you would like to know of one material, it doesn't help to study the individual components. One thing to add to this is what I've shown you up to now with this camera is only the self-emission from the plasma. So if you do pulse laser deposition, you always look into your system, you know the plasma and the colors it gives you. Depends on the elements, but this is self-emission. In your plasma are also elements which don't give you self-emission, which is still crucial. So the study that they did a few years ago was to look with laser-induced fluorescence. So here you can see that there was a dye laser over there, was shining to the system, and it was interacting with the plasma. So this blue one is the normal laser creating a plasma, and this dye laser was interacting with the plasma so that the CCD camera could also see about elements in the plasma which would show up because of the specific laser light which is used. And you have to choose this laser light depending on what kind of elements that you expect. that makes the story also complicated, because depending on, if you take a different target, you need a different laser. That's not possible. But here, to show the point, was that if you use different pressures, so let's say from 0.1 millibar to the lower numbers, on the right side you can see the self-emission moving forward. On the left side you can only see the titanium. So there you can see that the titanium is, some of them is moving forward, some of them is staying behind because of interaction within the plasma. But then you can really distinguish about where are specific elements happening and when are they oxidized. But this is nice because it shows you much more information, but it's a complex technique to use, as you need to adjust it for every material. Now, so if you look to pulse laser deposition, it's being mentioned very often as a simple technique, but there is a lot of specifics in it. These are a lot of the different parameters where you need to control. What I would like to do is to show you some examples. So you have seen studies before where people really use this to deposit single atomic layers of materials. This is something we did a couple of years ago, where you can see the neodymium gallium substrate, LSMO ferromagnetic layer, and then depositing one atomic layer of strontium titanate, determined heavily about the magnetic properties there. And if we do TEM, you can really see that only titanium in this layer, so you can really have this extreme control in the materials. And this is being used by a lot of different groups to create specific interfaces between different materials to control this. An interesting thing, maybe, I'm not sure how many of you are aware, but if you do pulse laser deposition, probably you get a lot of criticism about, cool for you make something on a centimeter, good luck, it's never been used in industry. I even had this from a referee to a paper of us. I said it's stupid because it doesn't tell anything about the fundamental research that we do. But these days, there is also, let's say the equipment that we use in the lab, this is coming from this company, it's a spin-off from our group since the 90s. But since more than 10 years, we also have this spin-off, Soulmates, which is selling equipment where they do this pulse laser deposition on 4-inch, but these days also towards 8-inch wafers. So if you ever get this question, point to this one, because this system is being used commercially, and as shown also by Professor von Pulin, is also working strongly in collaboration with IBM on projects. And they had a nice animation to show about how they were thinking about this. So on the front side, they said you have a system where you can put your silicon wafers in, but this is the main system here. So at the bottom you have your laser, and then you have an optical path bringing it into the system, and then you can deposit your materials. And the main focus of their equipment right now is to use it for PCT, for ferroelectric, piezoelectric applications. And these kind of equipments are now located, so we have one in the clean room, but there's also one at IMF, there's one at Syncadap, and are going to more places. The other thing what I want to show you is this picture you probably know. You want to grow a thin film, and you're looking for a substrate which fits as best as possible. So you have the smallest mismatch between them. And then you look, hopefully there is something available and you can get it from the supplier. It's not always easy, but it may be never perfect. And what we're looking into is situations where we want to grow on a surface which is not, we don't always want to use these exotic and expensive substrates. We also would like to show that you can grow some materials on plastics, or you can grow it on glass, or on some other situations. And what we do in a group, so this is expertise from Professor Tanelsov in our group, who's a chemist. What they do is they make materials. They start with particles. They can create so-called nanosheets, I'll show you in a minute, in a solution, and then they use Langmuir-Blodgett technique. It means in a solution, the nanosheets of 1 nanometer thin and micron size are floating on the surface. You dip your material into it, you pull out your material, and then the surface is coated with these nanosheets. And they form a template. So let's say on the surface you can see here, so this is a 2 micron scale, you can see all those sheets. They're in plane irregularly spaced, but they're all lying in the same direction as they're so thin. And with this you can create a very high coverage. And what you can do, you can, for instance, if you want to make titanium oxide nanosheets, you start with a specific material, and you do some protonation. You make that they all separate into nanosheets like this. They go into the liquid. Here you can see some pictures of it happening. But then you can create a surface which has a very high coverage, close to 100%. And one of the things that we did is we said we have all types of nanosheets, because if you want to grow a specific material looking for a crystal structure which matches. So one of the things we did, we deposited this on glass, and then we wanted to study cuprous oxide on glass. I'm not sure, you cannot even see the peak here. So I can show you. So this is how you normally have it on glass. There's almost no crystallity in the film. If you put the nanosheet layer in between, you do the same growth, and I think cuprous oxide was grown at 400 degrees. You can see the peak is here, to this point. Several orders of magnitude bigger, because you have a template which allowed you to grow this. In plane there is no alignment, although we're working on this. Now everything is pointing up, and for cuprous oxide, which is an interesting absorber material for solar cells and other things, this is the most important direction. So there's a lot of literature on this, on these nanosheets. And this is also an interesting thing where you can think about depositing oxides on all kind of other surfaces, going also towards maybe more industrial scale. One of the things that we did, not industrial interest, but really fundamental interest, is deposit thin films on TEM grids. So if you normally do that, you have a TEM membrane, there's silicon nitride, you deposit on this, and you just, terrible, because silicon nitride is not the best situation to grow. So what you can do is you put these nanosheets on top, it's a nice template, and then you can grow, for instance, vanadium oxide, and you can really, depending on this nanosheet, determine what type of crystal structure, because vanadium can be different, what's the orientation of that, and then you can do all kind of studies now in transmission mode. I won't go into detail, but what you could do is also, in this chemical processing, you can put lines of different types of nanosheets next to each other, and then if you grow vanadium oxide on top of them, what you see here is the outer plane crystal orientation, and it really shows if you have lines of different nanosheets, you can really tune the crystal orientation on top of them. And the in-plane, there is not so much control, because that's not what you're tuning, and that's where we can see that although you have some difference between them, it's never 100% perfect. But the outer plane is something that you control now very nicely. If you're interested to learn more about PLD, there are a lot of textbooks about this. Here I'm just flashing a couple of books. Some of them maybe are very known to you, which exist already for a longer time. The ones on the right, I've been involved, or some of my colleagues at Twente have been involved. And I put some of them also in the abstract, but if you would like to know more, you can ask me. I have some examples about more advanced PLD, which I would like to show you, but before I go there, are there any questions which you would like to ask right now? Yes?
Can you explain again what is the step flow growth regime?
Yeah, so if you have a surface and you have Terra steps, and you have a material where you deposit it and it has a lot of kinetic energy, so either you do this at higher temperatures so that when it arrives, it has sufficient energy to move over large distances, then it has also sufficient energy to move towards the step. Each time the material goes, moves, and hits the step. It means that it looks like the step is moving forward a little bit. So if you would look at this, it's more like the steps are flowing forward, instead of that you have something layer by layer, which is first 50% and then you fill up the holes. So it's really a surface with the same step density, but the step is moving forward. That's why the reed is not showing you anything, because the steps are always the same. There's a little bit of material arriving, moving to the step, and gets stuck.
So basically you don't see the reed oscillation because
you don't see oscillation. The only thing what you see is that you have a reed intensity, you have one pulse, so it drops a little bit, it comes back to the intensity. That's what I mean. In some systems, you have that the initial growth is layer by layer with oscillations, and then it goes into this mode. Looks like a constant, but you can still see all the individual pulses. The moment that you stop your deposition, you can see that it has a little bit more time, so the energy is a little bit higher. Yes. Yes.
About the step flow graph,
So my point is, if you would like to create a layer which is as smooth as possible, step flow could give you, if the material allows, and layer by layer could give you. Step flow is not a bad situation in this.
But if you want to make the multi-layer system or the super
Yeah,
system,
then the oscillations are very helpful to tell you how many layers and when to stop. Then step flow is not ideal.
but at the end, if the super structure or the multi-layer structure has this step flow like bulk mode, then is it better or?
No, it's not so much better.
Okay.
No, it could give you just a smooth surface.
So what about this intermixing?
No, that's not there's no difference between them. That's not because of that. Then it really depends on what are the energies which involve, what temperature do provide, and what's the interaction between those two materials if intermixing is energetically favorable at that moment. It's not only because of the step flow. How much time do we still have?
30 minutes.
How many?
Half an hour.
Okay, good. So what I would like to do is show you some of the more recent things that we have done. Where I would, yeah, so it's a different format. So I would like to call this that it's maybe more the advanced direction. So as a starting point, if we start combining materials, different types of materials, then in the end, and you could think of them as nano composites, where they're interesting from 2 points. So one of them is you combine 2 materials, and at least one of them is confined on the nanoscale. So if you have nano composites in ceramics, and there are lots of them, and we use them also in a lot of applications, you can think of this, for instance. You have small nanoparticles in a second material, and they're just in disorder way, they're everywhere. However, you could also think about these multi-layer systems and these super lattices, which maybe a lot of you also do form. But the third thing you could do is also form it in a vertical way. Maybe some of you are aware of this, and I'll show you some examples. This is something I would think which is very interesting, and what I've seen up to now, only PLD is able to do this through a self-assembly. Now let's say I start from the middle one, when you start into horizontal layers. I'm not sure how many of you are aware of this this paper. So the first author is in the audience, Hans Bosker over there. And what he did was he made this picture. So the picture is not like this in the paper, although Hans maybe wanted to do that, but that's why he's making a picture right now, because this is the way he wanted to show it, but he wasn't allowed. And what it does show, although you cannot read from this distance, but really look it up, it shows that you can take an enormous amount of oxide materials, but also 3-5 components to make beautiful multi-layer systems. And really tune these materials on the nanoscale. Really play with these individual materials, single unit cells, combination of them. And in the end you will get all kind of cool properties. And you have lots of examples in the literature. Over the years, I've also been involved in a lot of research where we make these super lattices. I think this started when I was a PhD student, just to show that we're capable of it, and when you do X-ray diffraction to prove that you had a very controlled system. But very often you can also have some very interesting properties with it. Now, several years ago, I got in contact with Chuck Fadley from the Advanced Light Source in Berkeley. And what their interest was that they're using all these X-ray techniques where they would like to study materials and specifically interfaces, but they were interested in a technique where they need a periodic system to create a standing wave. So they do X-rays, and if you have a periodic system, you can create a standing wave. And this standing wave, they can move through the material. And if the standing wave, let's say, is at a specific interface, it's extremely sensitive to this interface. So you can extract all kind of interesting things about interfaces, and interfaces are from all kind of points are interesting. So what he asked was, okay, can you make, you can do PLD, can you make me a periodic system with specific materials and thicknesses, and by the way, can you make as many periods as possible? I don't know how it happens for you, but if I make a super lattice after 10 periods, I think it's enough. It takes so much effort to do that. But for those people, that's not sufficient. So what we started doing was saying, okay, let's take lanthanum strontium manganite, the ferromagnetic material, let's take strontium titanate, start growing this where you make 4 unit cells each. So here you can see the reef, you can see oscillation LSMO, oscillation STO, LSMO, STO, on and on and on. And here, this is a zoom in, but you can see for LSMO it's going down each time, with STO it's going up, down, up. And here, each time you can see it going down and going up. Here you can see the time. 3 hours, 4 hours, this is after 16 hours. This was a super lattice buildup of 120 periods. And this took over the night, so I went to bed. The only thing which we did was we monitored it in the beginning, and then we told the computer, do these number of pulses and good luck with it. And the next morning we came back in. And this is what happened. So it deposited these number of pulses, and you can see this is pretty constant, and if I zoom in the last ones, it's still at this level. This is the read picture in the beginning of the substrate, and this is the read picture of the total superlattice. It's still a crossfire. So it's not 3D or there's no read picture, so we're still okay. By the way, all this is in one of those chapters of this book. And this is how the AFM of the surface looked like. So I'm not sure, but if you look from the back, you can still see a little bit of lines in it. So that's the direction of the steps, pretty far below, which is still visible on the top. And if you put a line over the surface, this is a height difference within a nanometer. So I would say it's still pretty smooth. So I was quite happy with this. So if you do X-ray diffraction in our labs, and this was with lab equipment, we can see here the superlattice peak, we can see some side peaks. So with the distance, we could confirm that this is also the periodicity that we were expecting. And if we zoom into this inner peak, you can also see some of the lower fringes telling you that you created some smooth system. Well, we're happy with this. And we did a lot of studies, and this was published. But in the end, we also looked with TEM. And this is the TEM picture, where you can see the substrate at the bottom, and you can see the top, and you can see all 120 periods. And I'm showing this more often if I talk about PLD. I was pretty happy with this, although when you are critical and you look at it, you can see it's never always perfect. But if you zoom in, you can see nicely the perovskite structure. In the intensity, you can say where is the lanthanum located, because it's more intense, and where's the other material. And it nicely shows this continuation of the perovskite structure. So you can really build up, and you can really make big structures out of this. And if you do TEM, you look in about where's the manganese, where's the titanium. Of course, this sample has a specific thickness, so you also have to think at these interfaces, maybe it's not 100% perfect. But then we looked a little bit into, okay, if you have that big picture, you can also extract what the individual thicknesses are of those layers, because I was aiming for 4 unit cells each. And when we looked into this, although there are some errors on top of it, which I'm not showing here, what the study showed is that although in the beginning I'm thinking that I'm growing 4 unit cells, but over the 16 hours or 120 periods, you can see that the thickness of all these layers dropped. With some errors on top of it, but the thickness of the samples, all this kind of, this was what was subtracted. Do you have an idea why the thickness dropped?
Aging?
Aging of the target. No, I don't think so. Yeah, I know, you know. Anybody else? So when you use a laser, pulse laser deposition, when you make your settings on the laser, what kind of mode do you use on the laser? Constant voltage or constant energy? Energy. Who's using voltage? Constant voltage. Constant energy. So with constant voltage, you have a much more constant pulse shape for each time. So constant voltage is something that we always use if we do our normal depositions. But it means that over time the energy is slowly decreasing because you're not correcting for this. That's my drop. What I didn't do for this one is to put it at constant energy to say, okay, maybe again the shape is not exactly the same, but at least I'm correcting over time for this. So I was amazed how much the drop could be for this time, but I don't know if it's exactly this, but at least you can see there is a decrease. So also that you have to be aware of how do you correct for this. If your deposition is taking a long time, if you do deposition for many hours, be aware that this could happen. Of course, we're also studying some other super lattices. So again, LSMO, as it grows beautifully and has interesting ferromagnetic properties, it's always an easy choice. But here we combine it with a superconductor, lanthanum strontium copper oxide. And this is, as it is superconductor, also interesting. But this lanthanum strontium copper oxide is a rock salt structure. And the rock salt structure, you can think of this as a much bigger structure, but it consists of two blocks, two charge neutral blocks. Which means that in your read, 2 oscillations count for a unit cell, this big unit cell. And here you can see that we grew LSMO with 7 oscillations, 7 unit cells, and this lanthanum strontium copper oxide with only 2 unit cells. And we built it up a superlattice. And here you can see in the second layer how that happened. The point was also that we used these conditions. We were not only interested for this, but also if I would grow my rock salt thicker, I would not be able to achieve the same quality because the rock salt, the mismatch was so big that it would form more roughness, and then I would not be able to form the superlattice. So I was limited by this, and I needed sufficient amount of LSMO to make everything, I would say, a little bit perfect. You can see the intensity always goes up a little bit. Now in the final structure, if you do TEM, you can see that this is also nicely arranged. The interest is because of this, this rock salt structure. If you look at the line, where the line is over here, on either the A or the B side, you can see the shift of these layers. Because that's the rock salt structure which either moves a little bit left or right. And in these studies, we looked at the interfaces, what's exactly happening, the bottom interface or the top interface, and see what's happening there. Now, over the years, we also have done a lot of studies on LEO, STO. I won't go into detail, but what we did as well, already, Otomo and Wang published this in Nature on a Thursday. On the Friday, with my PhD student, or with my master student, we said, let's do this as well, and let's grow these materials. Let's see if we can make a superlattice out of it. The results I'm showing you right now is not that first deposition, but already the first superlattice we made, we could see that, both of them can grow nicely in this way, and it was conducting. And then we did a lot of studies in the years after. But here you can see a superlattice where you can see the lanthanum aluminate being grown, several oscillations. You can see the strontium titanate grown. You can see in the second period. You can see even the 20th period, you can see the oscillations. And then we put the lanthanum aluminate on top. So these samples are being studied by the standing wave technique, where you're building the standing wave because of the superlattice. And in this way, in a controlled way, we can study the top interface between STO and LEO to see what's happening there. And we're working on a paper right now. But you can see that if you do this well, you can follow your read. And this was done manually. This is not, I didn't go to bed at this time. So this is where you can see if you set it in the beginning, you can still nicely follow all the individual oscillations till the end. And this is how the XRD from lab equipment shows that you have these superlattices, you have all these extra peaks, you have the fringes in between, which you can all model to extract the real structure that you have, which is important then to understand all measurements, standing wave measurements. Finally, what I want to show is the last part, only in a few slides, about these vertical nanocomposites. I'm not sure how many of you are aware, but in around 2006, first papers came out in Science, but this picture is from this advanced materials paper from a group from Ramesh, where they combined bismuth ferrite with cobalt ferrite, and they had them in a single target, ablated them on the surface, and under the correct conditions, it's self-assembled into a structure where you have one forming the pillars and the other one forming the matrix. And depending on the substrate, you can switch them. Either the cobalt ferrite is the pillar or bismuth ferrite is the pillar. And you can make beautiful structures, and afterwards a lot of other materials have been studied, and people look at what kind of effects are happening at the interfaces. You can now expect also strain at these vertical interfaces. Now, in my group we also study, most of our study is these days on lithium-ion materials, on battery-related materials. We'll talk about that on Saturday. And in batteries, you make stacks which are two-dimensional, where you say you want an anode, a cathode, an electrolyte in the middle, And if you want to have something with either high energy or a high power, you either have to choose if you make something with thin layers or you make it thick. Here can a lot of energy be stored, but they have to travel a far distance to get to the other side. Here they only have to travel a short distance, so a high power, but there is not a lot of energy. If you make a 3D structure, you can make a combination of both, which would be ideal. That you all have to travel a short distance, but with the pillars you can still create a lot of volume. Thinking that that's a specific unique capability of PLD, that's what we did. So we used two interesting, a cathode material and electrolyte, putting in a target, did a deposition, and on the back you can see the SEM picture from the surface. So you can see the square pillars are the spinel lithium manganese, and the matrix in between is the perovskite, lithium lanthanum titanate. And this was one of the first samples that we made. It grew beautifully already a couple of years ago, because we were still struggling to make it work as a battery. Because as it's formed this, I think there are a lot of strain effects at these interfaces, which is not ideal for the things that we want to achieve. If you make a cross-section, you can see that those spinel materials even point out the surface, as this is energetically most favorable, and the perovskite is in between. And from the colors in this, you can really see the two different materials. If we do X-ray diffraction, we can distinguish nicely these phases. And we're working on the first papers. If you go to different temperatures, you really have to go to higher temperatures to have these crystal phases to be formed. If you do the lower temperatures, you see that this is not so clear. And if you go higher, you can also see that these pillars become bigger. So if we do kinetic Monte Carlo simulation, kinetic Monte Carlo simulation of the two materials here on top of a strontium titanate surface, and we use niobium doped strontium titanate as it is conducting, using the read information of the individual materials and the energies which you can extract, then you can do modeling of how those will interact with each other to form these nanocomposites. So if you do them individually, you can see that the perovskite would like to grow as completely full thin films. Perovskite on perovskite is fine. The spinel doesn't like to wet, it doesn't like to diffuse, and it forms these much rougher pyramids sticking out. So that's what we see here as well. If we combine them, we get this. At low temperatures we can see more smaller structures, and when we go to higher temperatures we can see that the structures become bigger and much better defined. However, in these kinetic Monte Carlo simulations, we don't have limitations which also give you the specific formation of these square features. Where also more thermodynamics is involved. The other thing that we do is you take strontium titanate in the 001 orientation, and you can see what I've just shown you before, these cubes. This is the cross section. If we do 110, you get lines. You get very specific different features in your material, still 3D, still nicely connected to the bottom, but they look like rooftops, where the fusion along this specific crystal direction is much better than along the other one in plane. And what we're doing at the moment is really look into these interfaces between these two materials, so this is TEM, to see how these two materials are connected, because that's where lithium has to move from one side to the other to work as a battery. Which is not very successful right now, but we're looking into how to achieve that. Because also in these situations you have to really control the interfaces and maybe use some intermediate layers or anything. We have to think about it. So this is a picture of the cathode material, lithium manganese oxide. And what's nice about this, and these are data by Nicolas Gauguin from the University of Antwerp, where if you look in detail you can really see the lithium ions. Although they're very light, if you look into the structure, you can really distinguish both of them. And you can see that both of them are there, so this is a fully lithiated structure. And in the battery, this is what you normally change it. Put them in and you take them out. So, with that, I come to the end of my talk. And I would like to thank you and have some questions.